Hello everyone, my name is Peter Shields and on behalf of AirMet Scientific, I'm really pleased to welcome you to today's webinar, The Benefits of Continuous Ground Gas Monitoring over Spot Measurements. Today it's going to be presented by Peter Childs, the Vice President of International Sales from Iron Science. Peter's originally from Australia, but has been living in the UK and China for the past 11 years working with Iron Science. It's great to have him here in Melbourne today with me to do this presentation. So during the webinar today, if you have any questions, could you please just type them into the questions box and we'll do our very best to answer them at the end of the presentation. So I'd now like to hand over to Peter to run through his presentation.
Good morning everybody, and thanks for sharing your time with us today. First I'd like to just give a quick introduction to Iron Science, very brief one, and then we can move into the presentation itself. So Iron Science. Iron Science is a leading manufacturer of PID sensors. That's our core business, sensors and instruments. It's a private company. It was founded in 1989, so 30 years old. It's based in Cambridge in the United Kingdom. It's got group revenue of about £16 million, and it's got about 120 employees. As you can see here, we've got global coverage. The main factory and headquarters is based in Cambridge in the UK. We have subsidiaries in Houston, Texas, in the US, France, Germany, Italy, and Shanghai, where I'm currently based in China. So today we're going to talk about continuous ground gas monitoring and the benefits of continuous monitoring as opposed to spot monitoring for ground gas. Right. So, what is ground gas and what are the risks associated? So the problem with various hazards can arise depending on the gas released. What are these hazards? You have explosion hazards, health hazards, chronic long-term health effects, and you have global warming issues with some of the gases. So let's look at some of the sources. So ground gas can originate from natural and various forms of human activity. So a human activity might be landfill waste, abandoned coal mining, shale gas production, contaminated lands, and then of course pipeline leaks and coal bed methane, and also naturally occurring gas from naturally occurring sources. So these are some of the areas where we can have some gas release from both natural and man-made sources. Here we have just a few examples now, some case studies of some of the associated problems where a gas leak has occurred. So in this case in Abbotsford in 1984, there was natural methane from coal seams released into a water supply tunnel. So it's a cross between natural and man-made. This was pushed into the house after pumping began. The ignition source is not known, but a visiting group from the local community was present at the time of the explosion, and in this case it killed 16 people. More recently, and closer to home, there was an issue with the Cranbourne landfill site, and actually the methane was found to be leaking into residential areas in the local area, and this caused obviously a lot of associated risks, and obviously there was a lot of cost in the monitoring program, the remediation program, and in this case, the settlement after the situation was resolved. Losco in 1986, a house exploded. Fortunately, in this case, there was no persons present. They were away at holiday or something at the time. It was actually the gas had built up in an enclosed space in the house, and a heating system came on. The boiler was lit and it caused the explosion. We can see here, this is basically the geology of the site. So you've got the Losco landfill, and what we have to do when we look at a ground gas, we have to take into consideration the geography of the local area. And in this case, the landfill had been closed, so there was capping material on top of the landfill, and the geology had a limestone base where the ground gas could, or the gas being generated from the landfill, the closed landfill, could migrate through the limestone geology and collect in the housing estate. And over time, it's built up, and unfortunately, in this case, an ignition source was able to ignite the gas causing the explosion. So, what we want to look at when we're looking at monitoring for these potential hazards is we're looking at what are the environmental considerations need to be taken. So one of the environmental conditions is pressure and ambient temperature, ambient pressure, rain and snow, so rain and snow or frozen ground, and the water table, so the rise and fall of the water table. Spot check monitoring is therefore likely to miss some or all of the hazardous events because it's not monitoring continuously and might not account for or allow for the changes in these environmental conditions. So our objectives of ground gas monitoring is to determine the true subsurface gas regime, predict how this may change in the future. Currently, this is or has been achieved by discrete periodic measurements of ground concentrations and gas regime. So using spot measurements. So here we've got some data. This is a real sampling regime on a real site. So you can see here with the black measurements on around the 13th, 15th, and 28th of January of this year. We've taken spot measurements and we have quite low concentrations of, in this case, methane. Then on around the 15th, 23rd, and 29th of January, we have spot sample measurements that show quite high concentrations of methane. But in the spot sampling regime, we don't have any data in between. So the gas clam is able to fill in this data. So here there's been a gas clam at this site continuously monitoring during this period of time. And as you can see, the gas clam collects a lot more data. And you can also then calculate a basically concentration duration curve over this period and understand for what period of time is your gas at a higher concentration, say above 5% or 10%. So here's the actual unit itself. It's quite robust. It's made out of stainless steel. It's designed to go into the ground. It's obviously intrinsically safe and explosion proof. So the top part of the unit is explosion proof and the lower end is intrinsically safe. It's IP68, so in the event that there is inundation with water, the unit itself won't be compromised. It's been designed to fit a 50 mil borehole. The channels, you can mix and match what you want to actually monitor, but it can monitor methane, carbon dioxide, oxygen, hydrogen sulfide, VOCs, atmospheric pressure, borehole pressure. Can be deployed for up to 3 months on one charge. Without recharging the batteries or replacing the batteries. And this also is dependent on the sample regime and if you have telemetry. So it can vary, but anywhere from 5 weeks to 3 months. Okay, it's been designed to fit into, it was actually designed for British standards with a 50 mil borehole and then 150 mil top cover so you can securely place it in to the site itself. So here we have some data where we're looking at the methane relative to pressure. It's been generally understood that if you have a drop in pressure, you'll have an increase in gas generation from the borehole. This is not necessarily always the case, but it's quite often the case. And you can see here that we actually, in some parts of the graph, you can actually see that it's actually correlated quite effectively, where you have an increase in a drop in pressure and an increase in gas generation, but not necessarily always. And that might mean that there's some other environmental parameter that's actually affecting that correlation. Yeah, this is just showing you actually where we predict that if you have a drop in pressure, you can have an increase in methane. And then of course, like I was saying, this is not necessarily always the case. In this case, we're having a decrease in pressure, but also a decrease in methane being generated. So this is looking at a real site where we had closed landfill adjacent to housing. The example here shows no obvious change in methane when there's a change in ambient pressure. The gas clam also has the feature where you can monitor for groundwater. In this case, with the groundwater monitor accessory fitted, you can actually see that the cause in methane concentration variance was due to a rise in the water table. So this is obviously not necessarily in all applications, but where you have a fluctuating water table, it might have an effect on the ground gas coming out. Gas cans have also been used not necessarily just for landfills, which is what the unit was originally designed for, but also for fracking, which is the case we're looking at here. Credula is a large fracking company in the United Kingdom, and the site that they were going to frack is near a city called Blackpool, obviously a densely populated area. So the regulators wanted to ensure that fracking and the release and the use of some of the chemicals they use in the fracking process wasn't going to contaminate the local area, the residential areas, and not have any effect on the groundwater. And here's just a diagram of the actual hydraulic fracking process. So you can see there that water's pumped in to a borehole or a drilling hole, and high pressure water or fluid is pumped into a shale containing the gas, which is what they're seeking. That absorbs back into the fluid and is taken out for processing. The regulators want to ensure that that the fracking process wasn't going to release any of the gases into any other geological feature and be able to come out to the residential areas or drinking water. So here we've got some of the issues that has been experienced in the past when gas is released into obviously an area where it's not supposed to be. So the case study, the site's close to Blackpool and the surrounding towns and farms. Like I said, basically it was under scrutiny by local residents, politicians, and regulators. So what Credula decided to do was monitor the site before they began the fracking process, and then during the fracking process and after the fracking process, so that they could show the regulators and the local community that there was no effect. And here we can just see some of the data that was generated. So with the gas clam, you can monitor multiple channels. In this case, there were 21 gas clams used at 21 different sites around the area, and they built up basically a data profile of the sites and the ground gas that's coming out naturally over time and correlated to different changes in atmospheric pressure and water table, and whether or not the site was changing at different periods of time from summer to winter. And obviously in Blackpool and the north of England, the ground can freeze. So this was able to be presented to the regulators to show that there's no change. So prior to the fracking, so in the early part of 2012, and during the fracking and after the fracking in August of 2012. So a network of 21 gas cams was used. The monitoring, Mark, the CEO, so the monitoring device will allow us to collect background levels and compare them between before, during, and after operations. And obviously this is something that can be used to mitigate any concerns that regulators or local communities have with this kind of operation. Hierarchy cost benefit. So basically unmanned collection of data can be quite expensive. Another large utilization of gas clams was with the Q8 oil company. Q8, they had a problem with an operation that they had where large amounts of methane were released into a residential area. And initially what they had is they had 500 points they had to spot check on a daily basis. And they were using a spot check instrument. And so they had a team of people that were going out to each of these points and making a measurement. The information was found to be, it couldn't correlate any of the information or the data. It was found to be fairly unreliable, and there was no real way of actually determining how the gas is changing over time and where the source of the gas was actually coming from. So in this case, in the end, about 150 gas clams were used to build up a very detailed picture of the gas and how it was changing over time, how it was migrating through the soils, and an appropriate mitigation system was implemented, and this actually was able to remove the problem. Here's an example of a former petrol site, again in the United Kingdom. It was being remediated. A local house, the occupants of the house adjacent to the petrol station were complaining about smelling the VOCs and smelling or having an odorous smell in the house. During the day, the environmental consultants would come in, take a spot measurement, and they were basically measuring on average a VOC level that they didn't think was concerning. So out of frustration, the occupants of the house actually got onto GGES, Ground Gas Solutions in the UK, and they put a gas clam in the house. And Because they were able to collect continuous data, they were actually able to do a time average duration variation curve, as we can see here. And if you look at the data, you can see that actually during the nighttime, the concentrations of VOC were much higher than during the day. So when the people coming in taking their spot measurements during the day, they weren't able to see the higher readings of VOC, which the occupants of the house were complaining about, because actually it was during the night when, for whatever reasons, environmental or otherwise, they were having high levels of VOC. That's an interesting application that you can use with GasClam for getting continuous data as opposed to spot measurements. Another one, and this one's more so that we can show that if you are looking for VOC, the effects of H2S and CH4 on a PID sensor. So in this case, it's a water treatment facility in Singapore. The water treatment is for about 1.5 million people. In this case, the main purpose was to identify if industry is illegally discharging waste into the sewer systems. In this case, the GasClam was used to monitor a sewage point and to monitor for illegal discharge. So what we have to understand, firstly, that some gases that might be present, in this case H2S, will have an effect on a PID. So basically H2S is picked up by a PID sensor. And also if there's methane present, methane actually blocks the ability for a PID sensor to function. So this is the curve that, so you can see here, if you've got 5% methane concentration, then you're likely to lose 60% of a PID response. So in this case, we're using PID to monitor VOCs. H2S and CH4 must be also measured to validate the PID. False positives and negatives allow significant improved calculation of true VOC concentration if H2S and CH4 are present. So let's look at the following data. Here's the system. So you can see the GasClam is actually in this case attached to the fence on the right hand side, and a line is actually going from the GasClam into the sewer itself. So here's the raw data. So you can see here quite high concentrations of H2S. So that's going to cause the PID response to increase. And we also have some methane at the red chart there, which is going to cause the PID signal to decrease. So adjusting for this, the original VOC being the yellow. So using that, basically estimating the VOC, knowing what we know about the response of H2S and methane on a PID, we can get a more accurate reading for the actual VOC concentration, and that's shown in this chart here. Monitoring summary. So H2S and CH4 are present in the wastewater. Makes sense as both gases are produced by anaerobic bacteria. PID reading will be affected by these. By understanding how these gases affect PID reading, it is possible to estimate real VOC concentration. Without this, PID reading is meaningless. This allows to prevent health hazards and ensure personal safety, allow optimization of water treatment, identify if industry is illegally discharging wastewater, which is the primary cause for this use. And any questions? Thank you.
Okay, thanks, Pete. Yeah, if anyone's got any questions, if you'd just like to type them into the questions box. So there's a question is, how many gas clams do you need to effectively represent the gas regime across the site?
That's a difficult one. That depends on how big the site is, potentially what gases you might be looking at. Is it close to a residential area? What's the main purpose for doing the monitoring in the first place? So it's hard to answer a question like that because that's a little bit ambiguous. We found that, say for example, when we first put the monitoring system into the Q8 oil gas application, first we put out 20, and then we realized that actually we're probably going to need a lot more. And it just sort of, it grew up over time as we got more and more data. We understood that actually there's a few more areas that are causing the issue. So it's hard to say how many that you would need for a site. It's probably, you could start by doing continuous monitoring with 1 or 2 units, and then if you need more, you expand out from there. So the second question we've got is telemetry an option? It was with the gas clam 1, however, that's not an option at the moment with gas clam 2. But in saying that, we expect to have a telemetry option in the near future. So that is being worked on.
And that, if I can just add to that, I've spoken to our engineering manager, and he said it's possible for him to do that. It's on an individual basis and depending a bit on the site, based on whether the hazardous area locations and things like that. So, yeah.
Yep, we have the email refers to gas clam 2. What is the difference from the original version? The main difference is that we use our mini PID 2. That is effectively the only difference. A bit of the history with the gas clams. Einstein's was marketing and selling the gas clam for a number of years. We lost that in about 2014, and we regained that in 2018. So that's more of a marketing thing. The gas clam itself hasn't really changed that much since gas clam 1, except for the use of the mini PID 2, so the latest version of the PID.
So there's a few more questions there.
Accuracy versus lab analysis. We have a question asking, what is the accuracy of the unit in the field as opposed to lab analysis? And I don't have any data on that. So we'll put that.
I guess yeah, we can. I guess it would depend on there can be variations in the accuracy of lab analysis as well as accuracy of portable instruments and things like that. So there is in the specifications, the accuracy for the say CO2 is plus or minus 2% of, and yeah, there's various, but it's in the specification sheet that we'll send out after the in the post webinar email.
We have a question. How do you make the corrections when you have H2S and CH4 along with VOCs? Which factors do you use? I really probably have to ask Dr. Peter Morris for help on this one. We have a response factor for H2S that we know very well, and we have a curve for methane, how that attenuates the PID signal very well. So that's been used in this case, but I'm not the expert to ask on that one. I have to talk to Dr. Morris and calculation. Yeah, he's got a formula that he's used, obviously, and yeah, we'll probably put that on the email as well.
Yeah.
How much does it cost to install a gas clam? Does it involve any ongoing cost? There's two options, obviously. There's obviously the customer can rent the unit, and the customer can purchase the unit outright. The ongoing costs are changing the filters, and they get changed once every 3 months. Typically, I mean, it depends on the environment that it's in. So if you're purchasing it, I'm not sure how to answer that without,
yeah, there's no real cost to install it in, so far as it just fits into a standard bore.
The standard service and calibration costs on an annual basis, and that would depend on how many sensors are used as well. So I guess that's probably a question for a minute anyway, I guess.
Yeah, well, if you're interested in purchasing them or renting them, we can certainly get you some pricing for that. Yeah. Okay, that looks like. Oh no, here we go. Another one.
No. So the batteries, you can replace the rechargeable batteries every 3 months, or recharge them and then replace them. You can also use alkaline. They will only last for about 3 weeks, but it's always recommended to change the filter every time that you change the batteries. We have had in the past where filters weren't changed and the filter gets saturated, and then while the unit's still operating continuously, it then draws in fluids and moisture, and that has a problem inside the unit, obviously. Yep.
And the battery life is dependent on there's different batteries available that you can use, and also the setup of it, the number of sensors and the sampling frequency.
That's right. So you can change sampling frequency. There's also a minimum sampling frequency you can put in, but if you only need to get data once an hour or once every 6 hours, then the batteries obviously last a lot longer.
Okay, that looks to be all the questions. So thanks very much, everyone, for attending today. If you've got any further questions on anything that's discussed today, please feel free to contact any of your AirMet representatives. Finally, thanks, Pete, for your time today. Very informative and interesting presentation. So thank you very much.
Thank you.